Team Boron Delta presents PID tuning, the classical methods. The purpose of a PID controller is to regulate the output of a system to a user-specified set point by controlling one or more of the system inputs, or control variables. The controller accomplishes this by determining the error in the system output, as well as the derivative and integral of the error. Information is plugged into an equation which determines the controller output, or system input, necessary to return the system output to the set point. The objective of PID tuning is to determine the coefficients of the proportional, integral, and derivative error terms in the control equation, which provide the optimal control scheme. An optimal control scheme should be robust, responsive, and have minimal actuator activity. This is the general control equation. Here, U is the controller output, or the system input, E is the error, Kc, Ti, and Td are the coefficients we would like to determine. The Ziegler-Nichols and Tyrrell-Lubin methods both involve a similar tuning procedure, which require the determination of Ku, the ultimate gain, and Pu, the ultimate period. This is accomplished by operating the system under proportional control only and starting with a small value of Kc. A disturbance is then introduced into the system, which will cause an oscillation to occur. Kc is then increased incrementally, and the process is repeated until a sustained and stable oscillation in the system output is observed. Ku is the smallest value of Kc, which results in a sustained oscillation in the system output. Pu is the period of this oscillation. A correlation table can then be used to determine the correct values of Kc, Ti, and Td. This chart shows a situation where Kc is less than Ku. The oscillations die off, so Kc must be increased to find Ku. On this chart, Kc is too large. The oscillations are sustained but increase with time and fly out of control. Finally, this chart demonstrates the behavior of a system when Kc has been set to the value of Ku. The Cohen-Kuhn method is entirely different from either of the previous tuning methods. First, an impulse is generated in one of the system outputs, which is to be controlled. The system output is then monitored as a function of time. Several values must be calculated using this data, including the difference between the old and new steady-state output, B. This may require curve fitting or linear interpolation between data points. This plot represents the control variable, or the system input. A is the step between the old and new steady-state input. This plot shows the system response. B is the difference between the old and the new steady state. T2 is the time at which half of the new steady state is reached. T3 is the time at which 0.632 of the new steady state is reached. In conclusion, the Ziegler-Nichols, Tyrrell-Lubin, and Cohen-Kuhn tuning methods all provide a good initial guess of the PID tuning coefficients. Ziegler-Nichols and Tyrrell-Lubin require more experimentation and a control apparatus to already be in place. Cohen-Kuhn requires more data analysis, computation, and relies more on theory. Custom tuning should be used to optimize the control parameters for robustness and responsiveness using trial and error. Appendix A shows the equations and correlation table required to calculate Kc, Ti, and Td using the Cohen-Kuhn method. Appendix B shows the correlation tables for Ziegler-Nichols and Tyrrell-Lubin.